1,400 light years from Earth, there is a planet that takes 385 days to orbit its star. Its star is remarkably similar to our Sun. Its orbit places it at nearly the same distance from that star as Earth is from ours. And when NASA announced the planet in 2015, it immediately became one of the most intriguing Earth like worlds ever discovered. Its name is Kepler-452b, but this is not simply another distant planet sitting in a habitable zone. Kepler-452b is roughly 60% larger than Earth, placing it in a strange category of worlds that does not exist anywhere in our own solar system. Scientists cannot yet say with certainty whether it is a rocky super-Earth, a world wrapped in a thick atmosphere, or something fundamentally different. And its star carries an even more unsettling clue. Kepler 452 is roughly 1.5 billion years older than the Sun. Stars like ours slowly become brighter as they age. So, if this distant planet once began with conditions resembling Earth, it has already spent more than a billion additional years experiencing a future our own planet has yet to face. We cannot see its surface. We do not know whether it has oceans, continents, clouds, or even solid ground. The light reaching us from that system tonight began its journey roughly 14 centuries ago. We are not seeing Kepler 452b as it is now. We are looking into its past, and hidden inside that faint point of light may be something more revealing than another Earth. It may be a glimpse of what happens to an Earth like world when its sun grows old, a like, a subscribe, whatever feels right. It all helps this channel reach more people who love falling asleep to the sound of the universe. It starts with what astronomers actually discovered more than 1,000 light years from home. Kepler 452b has never appeared in a photograph. No telescope has resolved its continents, clouds, oceans, or horizon. The planet is overwhelmed by the brilliance of its parent star. What reached us instead was something far smaller, a repeating change in starlight, measured with extraordinary precision. That measurement came from the Kepler Space Telescope. On March 6, 2009, a Delta II rocket carried Kepler away from Cape Canaveral, beginning a mission built around patience. Rather than sweep constantly across the heavens, Kepler watched one fixed region. That field represented roughly 1/4 of 1% of the entire sky. Within it were approximately 150,000 stars. Kepler monitored their brightness simultaneously for more than 4 years, searching for tiny recurring dips. Each dip could mark a planet crossing between its star and the telescope. Astronomers call this the transit method. During a transit, a planet blocks a fraction of the light reaching us. Kepler 452b reduces its star's brightness by roughly 0.06 of 1% once every 385 days. That slight reduction contains remarkable information. The depth of a transit reveals how large the planet is compared with its star. The interval between repeated transits establishes the orbital period. Once astronomers know the star's mass, orbital mechanics allow them to calculate how far away the planet travels. We can reconstruct an orbit without ever seeing the world itself. Kepler was designed specifically for this task. Its photometer, the instrument measuring stellar brightness, could register changes comparable to detecting a moth crossing a distant car headlight. That sensitivity allowed researchers to search for relatively small planets around stars resembling our Sun, especially worlds whose orbits place them within potentially temperate regions. But one dimming is never enough. Instrumental errors, stellar activity, background stars, and eclipsing binary systems can imitate planetary transits. Researchers therefore need repeated events and independent observations before accepting a candidate. For Kepler 452b, several transits established the repeating pattern. Follow up work involving 12 ground based telescopes helped eliminate competing explanations. After years hidden inside the measurements, the planet was formally confirmed and announced on July 23rd, 2015. Yet confirmation establishes only certain things. The transit tells us about size and orbit. It does not show the color of the ground beneath any atmosphere. It cannot reveal weather systems, oceans, vegetation, clouds, or even whether a recognizable surface exists. Those details require observations beyond what we can currently obtain for such a distant target. So when we picture Kepler 452b, we are interpreting evidence rather than viewing scenery. Every physical portrait begins with that microscopic loss of starlight. From those recurring shadows, mathematics gives us a planet, an orbit, and boundaries on what that unseen world can plausibly be. The most revealing feature of Kepler 452 may be its age. At approximately 6 billion years old, this star has already spent far longer on the main sequence than our Sun. The difference is roughly 1.4 billion years. In stellar evolution, that additional time changes the environment surrounding a star. Kepler 452 belongs to the G2 spectral class, the same classification assigned to the Sun. Spectral classes organize stars according to properties including temperature and emitted light. Only about 7% of stars in the Milky Way belong to the broader G class. A close solar counterpart is therefore a relatively uncommon find. The similarities reach deeper. Kepler 452 is approximately 6% more massive than the Sun and about 10% larger in diameter. Its visible surface temperature is around 9,903 degrees Fahrenheit. The Sun's corresponding temperature is approximately 9,941 degrees Fahrenheit. Just 38 degrees separate them. If you could somehow view Kepler 452 from its planet, its familiar appearance might conceal the more consequential difference. The star would likely look slightly larger in the sky and subtly warmer in color than our Sun, yet its greater age has changed how much energy it releases. Kepler 452 is approximately 20% more luminous than the Sun today. That increased brightness emerges naturally from the physics governing stars like these. Deep inside a G type star, hydrogen nuclei gradually fuse into helium. As helium accumulates in the core, its internal structure changes. The core contracts and becomes hotter, allowing fusion to proceed under evolving conditions. Over immense spans of time, the star's total energy output rises. This progression is extremely gradual. A civilization living beneath such a star would never watch the change unfold within a lifetime. Geological records, oceans, atmospheres, and evolving ecosystems would experience its consequences across hundreds of millions of years. Our Sun follows the same underlying path. At roughly 4.6 billion years old, it occupies an earlier chapter of that evolution. Models of solar development indicate that another 1 to 2 billion years will bring its luminosity closer to the level Kepler 452 produces today. We are therefore observing a star resembling a later version of our own. That distinction matters more than the nearly matching temperatures suggest. Two stars can have remarkably similar visible surfaces while delivering different amounts of energy to their surrounding planets. Kepler 452 has spent billions of years changing by increments too small for any observer to notice directly. Its planet has remained beneath that evolving output throughout its history. Whatever conditions exist there now have developed under a star further along the same stellar pathway our Sun continues to follow. A year on Kepler 452b lasts 385, Earth days. If you marked its seasons on a calendar, the rhythm would seem strangely familiar. Only 20 additional days separate one complete orbit there from the cycle that organizes life on Earth. That resemblance begins with distance. Kepler-452b travels roughly 1.046 astronomical units from its star. Earth averages 1 astronomical unit from the Sunday. The distant planet, therefore, circles about 4.6% farther out than we do. Ordinarily, greater distance means less incoming stellar energy. Here, the older star changes the balance. Its greater luminosity more than compensates for those additional miles, leaving Kepler-452b with roughly 10% more stellar energy than Earth receives from the Sunday. 10% is significant, although it does not automatically make a world uninhabitable. An atmosphere can redistribute heat. Reflective clouds can send part of the incoming radiation back into space. Greenhouse gases can alter how efficiently energy escapes. With the right combination of atmospheric properties, a rocky planet could potentially remain temperate under that additional stellar input. The orbital timing creates another remarkable similarity. 385 days is close enough to our year that a 12-month calendar could still function with modest adjustments. If the planet has seasons, their individual lengths could occupy spans recognizable to human experience, although their intensity would depend on factors we cannot measure, including axial tilt and orbital eccentricity. Even the increased orbital distance would barely register from the surface. Light from the star would require only slightly more time to cross the intervening space than sunlight needs to reach Earth. Human senses would never detect that difference. These numbers attracted particular attention when the discovery was announced in 2015. John Jenkins, who led the Kepler data analysis team, emphasized how closely the planet's orbit resembled Earth's. At the time, the National Aeronautics and Space Administration described Kepler-452b as the closest known analog to our planet around a sun-like star. There is nothing mysterious behind the resemblance. With enormous numbers of planetary systems throughout the galaxy, some orbital arrangements should eventually resemble ours closely. What makes this case unusual is how several measurements converge at once. The orbital distance differs by only a few percent. The year differs by 20 days. The star belongs to the same broad stellar family as our Sun, while supplying somewhat more energy because of its greater luminosity. So if you followed Kepler-452b around one complete revolution, the clock of that journey would feel unexpectedly recognizable. The orbit traces a familiar cadence around an older star, preserving the geometry of Earth's year while placing the planet under a different energy budget. Imagine enlarging Earth until its radius grows by 60%. The change sounds modest when expressed as a single percentage. In 3 dimensions, however, size compounds rapidly. Kepler-452b has a measured radius approximately 1.6 times Earth's, giving it roughly 4 times our planet's volume. Its surface area would be around 2.5 times greater. If the planet possesses continents and oceans, they would spread across a world with vastly more surface available than Earth. Yet size alone cannot tell us what occupies that surface or whether a conventional surface exists. Mass is the harder measurement. Astronomers have no confirmed radial velocity measurement for Kepler-452b. Radial velocity detects the tiny gravitational motion a planet produces in its star, allowing researchers to estimate planetary mass. Without that measurement, scientists must rely on models connecting radius with likely composition. Those models commonly place Kepler-452b somewhere around 3 to 5 Earth masses. If it is rocky and falls within that range, gravity at the surface could reach roughly 1.4 to 1.9 times Earth's gravity. You would notice immediately. A person weighing 180 pounds on Earth could weigh between 252 and 342 pounds there. Every movement would demand more effort. Falling objects would accelerate more strongly, while geological structures would carry greater loads under their own weight. Gravity would influence the entire planet. Mountains could be lower and broader because tall formations become harder to support. Atmospheric gases would be held more tightly. Clouds could form under different pressure conditions. Water would settle within a gravitational environment unlike Earth's, while the planet's interior could experience different patterns of mantle movement and tectonic activity. But the largest uncertainty begins with the planet's radius itself. Exoplanets, around roughly 1.5 to 2 Earth radii, occupy an important transition region. Smaller worlds are frequently rocky. Larger ones often retain substantial envelopes of hydrogen and helium acquired during formation, producing planets more closely resembling small versions of Neptune. Astronomers commonly call worlds in this general mass range super-Earths. The term describes planetary scale, however, and does not guarantee an Earth-like surface. Kepler 452b sits almost directly inside this uncertain territory. At approximately 1.6 Earth radii, its measured size cannot distinguish confidently between an enormous rocky world and a planet wrapped beneath a deep gaseous envelope. Composition models place its probability of being rocky at roughly 49 to 62%, depending on the assumptions used. That leaves us with an unusual boundary in our portrait of this planet. We can calculate its enormous dimensions from starlight with impressive precision, while the same measurement leaves roughly even odds that beneath its atmosphere there may be no solid ground resembling Earth's at all. The habitable zone is often pictured as a narrow green band around a star. That image is useful, but incomplete. In reality, its boundaries depend on changing stellar energy and the atmosphere of whatever planet happens to orbit there. At its simplest, the habitable zone describes distances where liquid water could potentially remain on a planetary surface. It says nothing about whether water actually exists there. It also tells us nothing about life. A barren planet can occupy the habitable zone, while an unsuitable atmosphere can make an otherwise promising orbit hostile. Researchers, therefore, work with different boundaries. The conservative habitable zone applies stricter climate limits. Near its inner edge lies the runaway greenhouse threshold. Here, increasing heat drives greater evaporation. Water vapor strengthens greenhouse warming, encouraging still more evaporation until stable surface oceans may become impossible. The outer boundary presents the opposite problem. Carbon dioxide can warm a cold planet only so effectively. Far enough from the star, additional carbon dioxide may begin condensing rather than providing sufficient greenhouse warming. Surface water then becomes increasingly difficult to maintain in liquid form. Kepler 452b occupies a more complicated position. Depending on the climate assumptions used, researchers place it within an optimistic habitable zone, a broader region allowing favorable planetary feedbacks. Reflective cloud cover, atmospheric circulation, and surface reflectivity could alter how much incoming energy becomes retained heat. That reflectivity has a name: albedo. A bright cloud deck has a high albedo because it reflects substantial starlight. Darker surfaces absorb more energy. Two planets receiving identical stellar radiation can therefore develop very different climates. This is why orbital distance alone cannot settle habitability. Kepler 452b lies toward the warmer inner portion of the relevant zone. Its location remains potentially compatible with surface water under some models, yet the energy arriving from its star places greater demands on whatever climate regulation the planet possesses. There is another complication. Habitable zones move. A planet can maintain essentially the same orbit for billions of years, while its relationship to the habitable zone changes. As a sun-like star ages and becomes more luminous, the inner boundary gradually shifts outward. Researchers sometimes describe this long movement as habitable zone creep. Earth participates in the same process. Our planet currently occupies a favorable region around the Sun, but that arrangement is temporary on geological timescales. As solar luminosity rises during the next billion years, Earth's position will become progressively closer to the warming inner boundary, without Earth needing to move significantly closer to the Sunday. Kepler-452b has experienced this stellar evolution for roughly 1.4 billion years longer. Its orbit may have remained remarkably stable, while the habitable conditions associated with that orbit gradually shifted around it. A world can therefore stay in place while the region capable of supporting surface oceans slowly passes beyond its path. A billion years ago, Kepler-452b may have occupied a very different climate regime. Its orbit could have remained almost unchanged, while the star above it gradually grew brighter. Under several models, the planet may then have rested comfortably within the conservative habitable zone, receiving conditions closer to those Earth experiences today. Time altered that balance. Kepler 452 continued aging, and its energy output increased. Today, Kepler 452b receives an estimated 10% more stellar energy than Earth receives from the Sunday. That figure will continue rising as the star advances through its main sequence lifetime. For an Earth-like world, 10% matters enormously. Climate models place important greenhouse thresholds within roughly 5 to 10% above Earth's present solar input, although the exact boundary depends strongly on atmospheric conditions. Kepler 452b may therefore be approaching that threshold, or it may already have crossed it. If surface oceans exist, warming increases evaporation. More water enters the atmosphere as vapor, and water vapor is itself a powerful greenhouse gas. The atmosphere then retains additional heat. That extra warmth drives further evaporation, placing still more water vapor overhead. Eventually, the feedback can sustain itself. Scientists call the extreme outcome a runaway greenhouse. Once established, surface temperatures rise until stable oceans can no longer survive. Water increasingly occupies the atmosphere, where intense stellar radiation can break its molecules apart. Over geological time, hydrogen may escape into space, gradually removing part of the planet's original water inventory. We have a nearby example of where such climate evolution can lead. Venus may once have supported surface water for a substantial portion of its early history, perhaps for as long as 2 billion years, according to some models. Today, its surface reaches around 900 degrees Fahrenheit beneath atmospheric pressure, approximately 92 times Earth's. Kepler 452b cannot simply be assigned the same fate. We do not know its atmospheric composition, cloud coverage, geological carbon cycling, or surface reflectivity. Highly reflective clouds could reduce absorbed stellar energy. Geological processes might regulate greenhouse gases across immense periods, A different atmospheric structure could shift the critical threshold substantially. That uncertainty matters. Still, stellar evolution itself is secure physics. Kepler-452 was dimmer in the past, and it will become brighter with time. Its planet has therefore experienced an increasing energy supply regardless of whatever climate developed below. The comparison eventually returns to our own sky. Our Sun is following the same evolutionary process, approximately 1.4 billion years behind Kepler 452. Earth currently occupies an earlier stage of that stellar timeline. Given enough time, increasing solar luminosity will place our oceans and atmosphere under the same basic physical pressure now confronting any Earth-like environment that may exist on Kepler 452b. Life changes the meaning of a billion years. On Earth, that span contains entire biological revolutions, vanished ecosystems, and evolutionary branches with no living descendants. Kepler 452b may have had roughly 1.5 billion additional years for such processes to unfold, assuming suitable conditions ever existed there. That assumption matters. We have no evidence that life exists there now, or that it ever began. Yet Earth's history gives us a timeline for exploring the possibility without treating speculation as observation. Our planet formed about 4.5 billion years ago. Evidence places early life at roughly 3.5 to 3.8 billion years ago, meaning biology emerged within approximately 700 million years of Earth's formation. If Kepler-452b formed alongside its older star and life arose at a comparable pace, biology could have appeared there around 5 billion years ago. From there, the scale widens. Complex multicellular organisms appeared relatively late on Earth, around 600 million years ago. Applying that same developmental timing to Kepler-452b would place comparable complexity roughly 2.1 billion years into our past. This parallel is hypothetical, since evolution follows circumstance rather than a universal schedule. Still, it shows what an additional 1.5 billion years actually permits. Tool using human ancestors emerged only within the last few million years. Writing arrived roughly 5,000 years ago. Our technological civilization occupies a microscopic fraction of Earth's biological history. Now imagine adding 1.497 billion years after technological intelligence appears. That interval exceeds the entire span separating Earth's earliest complex multicellular organisms from you listening today. Compared with 5,000 years of writing, 1.5 billion years is approximately 300,000 times longer. No reliable model can describe what technology would become across such a duration. Civilizations might collapse, stabilize, transform beyond recognition, leave their planet, or disappear entirely. Biological evolution itself could continue alongside technology until familiar categories such as species and civilization lose much of their present meaning. This is where the Fermi paradox becomes unusually specific. The Fermi paradox asks why a universe apparently capable of producing many potentially habitable worlds has yielded no confirmed evidence of extraterrestrial technological civilizations. Kepler 452b gives that question an address. Perhaps life never began there. Perhaps biology emerged, but never produced technological intelligence. A civilization may have existed and disappeared as planetary conditions changed. Something could even remain there today while producing no signal our instruments can recognize across 1,400 light years. We cannot choose among those possibilities from existing evidence. The enormous head start only establishes time, and time guarantees nothing. Yet, if biology ever gained a foothold on that distant world, evolution may have received a span unavailable to Earth's biosphere so far. Suppose the rocky interpretation is correct. Somewhere beneath the glare of Kepler-452, there would be actual ground, shaped by gravity, geology, atmosphere, and perhaps water. Physics lets us sketch that landscape, although every feature remains an extrapolation rather than an observation. Gravity would dominate the experience. If the planet has between 3 and 5 Earth masses, its surface gravity could range from roughly 1.4 to 1.9 times Earth's. That stronger pull would compress the atmosphere toward the ground, potentially creating a denser column of air and greater surface pressure. The terrain would respond as well. Mountains can rise only while their underlying rock supports their weight. Under stronger gravity, towering formations become harder to sustain. Peaks might therefore grow lower and broader than Earth's Himalayas, with massive slopes spreading across greater distances before geological stresses force the crust downward. Water, if present, would obey the same stronger pull. Oceans could spread across broad basins rather than concentrating as deeply as Earth's seas. Trenches might become proportionally shallower, while coastlines could extend around immense lowlands. The exact arrangement would depend on crustal structure, tectonic activity, and the planet's total water inventory. Above that landscape, the sky remains another uncertainty. Color depends heavily on atmospheric chemistry. If nitrogen and oxygen dominate as they do on Earth, shorter wavelengths of visible light would scatter through the air and could produce a blue sky. A thicker atmosphere might scatter light more strongly, creating a deeper blue appearance, perhaps shifting subtly toward violet under certain compositions and lighting conditions. Then there is the horizon. Because Kepler-452b has roughly 1.6 times Earth's radius, its surface would curve away more gradually beneath you. On level terrain, the horizon would lie farther away than it does on Earth. Vast plains or oceans could therefore appear especially expansive, with planetary curvature becoming less apparent across ordinary human viewing distances. How long would daylight last? We do not know. No measurement has established the planet's rotation period. A day could last 10 hours, 40 hours, or something outside that range. Rotation would strongly influence atmospheric circulation, temperature differences, storm organization, and the movement of weather across the surface. Greater incoming stellar energy could add further power to that circulation. If liquid water and a substantial atmosphere survive, evaporation might become more vigorous. Clouds could build differently, precipitation cycles could intensify, and storms might redistribute heat across enormous distances. Yet none of these landscapes has been seen. At roughly 1,400 light-years away, Kepler-452b remains beyond our ability to resolve at surface scale. No existing instrument can verify its mountains, oceans, clouds, or sky. What we can construct is a physically plausible world, constrained by measured size and orbital properties. While its actual surface remains inaccessible to observation, an atmosphere can turn the same amount of starlight into entirely different worlds. Around Kepler-452b, that invisible layer may determine whether water survives, whether temperatures remain moderate, and whether the surface has become something closer to a steam-dominated environment. We have never measured that atmosphere directly. The transit observations reveal the planet's dimensions and orbital behavior, but they cannot tell us which gases surround it. That missing information leaves climate as the largest unresolved variable in the planet's story. Earth shows why composition matters. Our climate participates in the carbon silicate cycle, a geological feedback that regulates carbon dioxide over immense periods. When temperatures rise, rainfall and chemical weathering remove carbon dioxide from the atmosphere. Carbon becomes incorporated into minerals and eventually carried into Earth's crust. Plate tectonics helps complete the cycle. Material moves through the interior, while volcanic activity eventually returns carbon dioxide to the atmosphere. This process unfolds across millions of years, creating a planetary thermostat that can resist gradual changes in solar energy. If Kepler-452b possesses active geology and a comparable cycle, its climate might have remained stable longer than calculations based only on incoming starlight suggest. The planet could respond to increasing stellar energy by reducing atmospheric carbon dioxide, weakening greenhouse warming. But that thermostat requires the right conditions. Liquid water plays a central role in rock weathering. Once surface water disappears, the mechanism can weaken dramatically. Venus illustrates the danger. Its present environment lacks the water-driven weathering system that helps regulate Earth's atmospheric carbon dioxide, allowing an enormous greenhouse atmosphere to persist. Kepler 452b introduces another complication through stronger gravity. Greater gravitational pull would make atmospheric escape more difficult, helping the planet retain lighter gases. Hydrogen produced high in the atmosphere could therefore escape differently than it does from a smaller world, altering the long-term evolution of water and atmospheric chemistry. Clouds add another uncertainty. Their effect depends on altitude, thickness, composition, and coverage. Bright clouds can reflect substantial incoming energy before it warms the surface. Some climate models suggest strong reflective cloud feedback could preserve temperate conditions even when a planet receives 10 to 20% more stellar energy than Earth. We cannot determine whether that protection exists there. The James Webb Space Telescope can study certain exoplanet atmospheres through transmission spectroscopy, which identifies gases by examining wavelengths absorbed as starlight passes through atmospheric layers. This technique works especially well for nearby planets crossing smaller stars. Kepler 452b presents a far harder target. Its great distance and sun-like host make the atmospheric signal too faint for meaningful characterization with present instruments. So, the variable controlling nearly every climate scenario remains unmeasured. We know where the planet travels and how much starlight reaches it. Whether that energy falls upon a regulated atmosphere, a dense greenhouse, or something entirely different remains beyond our observational reach. Our solar system contains a missing category of planet. Earth sits at 1 Earth mass, while Neptune rises to roughly 17. Between them lies a broad planetary range with no local example, even though observations show that such worlds are widespread elsewhere. Astronomers call many of them super-Earths. The term generally describes planets more massive than Earth, yet substantially below Neptune, often spanning roughly 1 to 10 Earth masses. It sounds like a larger version of our world, but the name says little about actual surface conditions. A super-Earth can be rocky, ocean-covered, or wrapped beneath a deep atmosphere. Kepler revealed just how common these intermediate worlds are. Across thousands of planetary systems, planets larger than Earth and smaller than Neptune appeared repeatedly. They became one of the dominant populations in the mission's discoveries, showing that our own planetary arrangement is unusual in lacking one. Then astronomers noticed something stranger. In 2017, astronomer Benjamin Fulton and colleagues identified a statistical feature now called the Fulton gap, also known as the radius gap. Planets appear less common within a narrow range, separating larger rocky worlds from smaller Neptune-like planets. The transition occurs around roughly 1.5 to 2 Earth radii. Below this region, planets are more likely to have rocky compositions. Above it, many worlds retain substantial envelopes of hydrogen and helium, creating lower density planets with thick atmospheres surrounding smaller interiors. Kepler 452b sits near this divide. With a radius around 1.6 times Earth's, it occupies precisely the territory where composition becomes difficult to predict from size alone. Its dimensions are therefore more than a measurement of scale. They place the planet near a physical boundary between two fundamentally different kinds of world. Planet formation helps explain that boundary. Young planets gather material from disks of gas and dust surrounding newborn stars. Sufficiently massive worlds can capture hydrogen and helium before the surrounding disk disperses. Later, intense radiation may strip some atmospheres away, leaving smaller, rocky cores exposed while larger planets retain their gaseous coverings. If Kepler 452b remained rocky, its greater mass could also alter its internal behavior. More retained heat might support vigorous mantle convection, volcanism, and long-lived geological activity. Those processes could influence atmospheric chemistry and climate across billions of years. Different interior pressures, however, might produce geological behavior unlike anything observed on Earth. We have no direct experience with such a planet. Every spacecraft humanity has landed on another world has explored bodies with surface gravity equal to or weaker than Earth's. No rover has crossed a super-Earth. No lander has measured its ground beneath stronger gravity. Kepler 452b therefore occupies a planetary class that appears common across the galaxy, yet remains absent from our immediate neighborhood. We recognize the category statistically, while the physical experience of standing on such a world remains entirely beyond human observation. There is a useful boundary running through everything we know about Kepler 452b. On one side are measurements recorded from light. On the other are conclusions built from physics, statistics, and planetary models. Keeping those categories separate matters because certainty changes sharply when we cross that line. Start with observation. Kepler measured an orbital period of approximately 384.84 Earth days. The planet's orbital semi-major axis, meaning its average orbital scale, is estimated at about 1.046 astronomical units. Its measured radius is approximately 1.63 Earth radii, with an uncertainty of about 0.23 Earth radii. The host star is better characterized. Kepler 452 is a sun-like star of the same broad spectral class as our Sunday. Measurements indicate that it is roughly 6% more massive, about 10% larger, and around 20% more luminous. Its age is estimated near 6 billion years, approximately 1.5 billion years beyond the Sunday. Surface temperature is close to 9,900 degrees Fahrenheit. Those observations provide the foundation. Models supply much of the rest. From the star's luminosity and the planet's orbit, researchers estimate that Kepler 452b receives roughly 10% more stellar energy than Earth. A simple equilibrium calculation, which estimates temperature before atmospheric greenhouse warming, is considered, places it near 8 degrees Fahrenheit. Mass remains less secure. No confirmed radial velocity measurement has directly weighed the planet, so estimates commonly place it around 3 to 5 Earth masses. From those assumed masses and the measured radius, surface gravity could fall roughly between 1.4 and 1.9 times Earth's gravity. Composition becomes even less certain. Statistical models have placed the probability of a rocky composition around 49 to 62%, depending on the assumptions used. That means the familiar rocky landscape we might imagine remains only one scientifically plausible possibility. Then we reach the unknowns. No observation has revealed the atmosphere's composition, thickness, or even confirmed its presence. We do not know the actual surface temperature. Liquid water has never been detected. Surface pressure remains unknown. So does the planet's rotation period. We have detected no moons around it. Its magnetic field cannot currently be measured, leaving another major uncertainty about how effectively an atmosphere might resist erosion from stellar particles. Most importantly, there is no evidence showing whether life exists there now, existed there previously, or ever began at all. This distinction does not diminish Kepler-452b. It gives the discovery its proper scale. We possess a remarkably precise orbital outline from about 1,400 light-years away, while nearly everything occurring beneath that distant point of starlight remains beyond direct observation. By the time Kepler stopped watching its original star field, the mission had accumulated something more valuable than a collection of discoveries. It had created a census. Across years of repeated measurements, the telescope recorded stellar brightness with enough consistency to reveal planetary systems hidden inside an immense archive of light. The primary mission began in 2009 and continued until 2013. That year, the failure of a second reaction wheel ended the spacecraft's original precision pointing capability. Engineers found another way to use it. Reconfigured as the Kepler-2 mission, the telescope observed different regions along the ecliptic until 2018, when dwindling fuel finally ended operations. Its observations continued working after the spacecraft itself stopped. Data from Kepler and Kepler-2 have contributed more than 2,700 confirmed exoplanets, while additional candidates have remained available for continued investigation. The archive is enormous because roughly 150,000 stars were monitored during the original survey, with brightness measurements commonly recorded about every 30 minutes. No small research team could inspect every pattern manually. The Planet Hunters Citizen Science Project therefore invited members of the public to examine Kepler light curves, graphs showing how stellar brightness changes with time. Human eyes sometimes noticed patterns automated searches overlooked. Professional astronomy had effectively gained thousands of additional observers, all working through the same stored measurements. Kepler-452b emerged from this wider catalog. In July 2015, its announcement came with a new group of planetary candidates, while Kepler-452b became the most prominent example because of its unusually Earth-like orbital setting. Yet the mission was never built around finding one symbolic world. Its observing field pointed toward Cygnus, where Kepler watched a narrow region containing stars within our part of the Milky Way. Kepler-452 lies in the same broad spiral structure that contains the Sun, often called the Orion Arm. At roughly 1,400 light-years away, it remains distant by human standards, yet it belongs to our wider galactic neighborhood rather than some remote edge of the galaxy. That context changes how we read the discovery. Kepler found thousands of worlds with sizes and orbits unlike anything represented in our own solar system. It also revealed smaller planets and showed that planetary systems are widespread. Estimates derived from the survey indicate that potentially temperate, roughly Earth sized worlds could number in the billions across the Milky Way, although the exact frequency depends on how size, stellar type, and habitable zones are defined. So when you picture Kepler 452b, you are seeing one recognizable member of a much larger statistical population. Its importance comes partly from resemblance. The deeper result is that Kepler transformed planets from rare discoveries into a population we can measure. A distance can become so large that it stops behaving like geography. Kepler 452b lies about 1,400 light years from Earth. That means every observation we receive is ancient. The light reaching our instruments today began crossing space roughly 14 centuries ago. If light left the planet now, Earth would receive it around the year 3426. Nothing carrying information can outrun that limit under known physics. A message transmitted toward the system would need about 1,400 years to arrive. Any reply sent immediately would require another 1,400 years. One exchange would therefore span roughly 2,800 years from our perspective. Spacecraft make the separation far harsher. Voyager 1, humanity's most distant spacecraft, travels through interstellar space at roughly 38,000 miles per hour relative to the Sunday. If a craft maintained that speed toward Kepler 452b, the crossing would require roughly 25 million years. Human history barely registers against such a duration. More ambitious ideas change the numbers, yet not the basic reality. Breakthrough Starshot has explored the concept of pushing tiny light sails with powerful ground-based lasers. The proposed target speed is around 20% of the speed of light. At that velocity, crossing 1,400 light-years would still take approximately 7,000 years, as measured from Earth. Relativity would begin altering the passage of time aboard such a journey. At 20% of light speed, time dilation means a traveler would experience slightly less time than observers remaining on Earth. But the difference is modest. Thousands of years would still pass aboard the vessel even before considering acceleration, navigation, shielding, maintenance, and deceleration. And those problems grow rapidly with mass. Accelerating a wafer-sized probe is profoundly different from accelerating a ship carrying people, life support, shielding, supplies, and propulsion equipment. Kinetic energy rises steeply as velocity increases. Interstellar dust also becomes dangerous at extreme speeds because tiny impacts release enormous energy. No existing propulsion system can carry humans anywhere close to Kepler 452b on a civilization scale. Even reaching 1% of light speed with a massive crewed spacecraft would demand extraordinary energy, while slowing down at the destination creates another major requirement. We cannot solve the distance simply by building a larger rocket. So you can place Kepler 452b on a star map. We can measure its orbit from Earth and infer properties from its distant light. Yet physically reaching it belongs to a different category entirely. The planet can resemble our world in remarkable ways while remaining separated from us by a wall written directly into the scale of space and the speed limit of the universe. Life can alter a planet without ever sending a message. On Earth, organisms have reshaped the atmosphere for billions of years, leaving chemical patterns that could, in principle, betray our presence across interstellar space. Astrobiologists search for comparable patterns elsewhere using remote spectroscopy, the study of matter through the wavelengths of light it absorbs or emits. These atmospheric clues are called biosignatures. Oxygen is one important example when present in large quantities, although oxygen alone does not prove biology. Methane can provide another clue. When methane and oxygen occupy the same atmosphere, chemistry tends to remove them over time. Finding both in persistent abundance could indicate that some process continually replenishes them. Ozone and nitrous oxide can also become useful pieces of a larger chemical picture. Earth demonstrates why combinations matter. Roughly 21% of our atmosphere is oxygen, while methane exists only in trace amounts. Ozone forms through reactions involving oxygen higher in the atmosphere. Taken together with environmental context, these gases reveal a planet maintained far from simple chemical equilibrium. Life is a major reason that imbalance persists. Astronomers can sometimes investigate such chemistry during a transit. As a planet crosses its star, a thin portion of starlight passes through the planet's atmosphere before reaching us. Atmospheric molecules absorb particular wavelengths. The missing portions form spectral fingerprints, allowing instruments to infer which gases intercepted the light. This technique is called transmission spectroscopy. The James Webb Space Telescope can perform this work for favorable exoplanets. Kepler-452b, however, presents an exceptionally difficult target. Its star resembles the Sun, so the planet is small compared with the bright stellar disk behind it. The atmospheric layer is smaller still. That makes its spectral imprint vastly harder to separate from stellar light and instrumental noise than the signal from a planet crossing a small red dwarf. Distance compounds the problem. At roughly 1,400 light years, Kepler-452b delivers very little usable atmospheric information to our instruments. Even Earth-like biological activity could remain completely hidden within the available signal. A living surface might transform an entire atmosphere while leaving us unable to distinguish its fingerprints. Future observatories will push closer. The extremely large telescope in Chile and the proposed 30-meter telescope are designed to study faint worlds with capabilities beyond today's ground observatories. Their strongest opportunities for detailed atmospheric work involve much nearer planetary systems, where more photons reach our detectors and repeated observations can build stronger signals. For Kepler-452b, that advantage disappears across 14 centuries of traveling light. We can identify its passage across its star and estimate important orbital properties. But if forests, microbes, oceans, or some unfamiliar biology are altering its atmosphere, present technology cannot reveal them. For the foreseeable future, life there could be abundant, absent, or long vanished, and all three possibilities would look essentially the same from Earth. A radio telescope does not listen for voices in the ordinary sense. It searches an immense electromagnetic spectrum for patterns that nature may struggle to produce. Narrow signals, repeating structures, or transmissions drifting predictably with planetary motion can become technosignatures, measurable evidence suggesting the presence of technology. That idea has shaped the search for extraterrestrial intelligence for decades. After Kepler-452b was announced in 2015, the system became an obvious target for radio observations. The Allen Telescope Array examined the direction of Kepler-452, searching for artificial radio emission. No convincing extraterrestrial transmission emerged. Other searches have examined planetary systems within Kepler's field using the Green Bank Telescope in West Virginia, one of the world's largest fully steerable radio telescopes. These surveys have searched narrow portions of the radio spectrum with extraordinary sensitivity. They have produced enormous numbers of candidate signals, only for careful analysis to trace them to human technology, interference, or other terrestrial sources. So far, no verified artificial signal has been detected from Kepler-452. But that statement covers only what our instruments actually tested. Radio searches sample particular frequencies during particular observing windows. A transmitter could operate outside those frequencies, broadcast intermittently, aim elsewhere, or use power too weak for Earth to detect. Even an intentional beacon could escape notice if we happened to observe while it was inactive. Astronomers sometimes describe this limitation as the cosmic haystack problem. Imagine every possible direction, frequency, bandwidth, transmission strength, polarization, timing pattern, and signal type as part of one enormous search space. Humanity has inspected only a minute portion of it. Finding nothing inside that fraction tells us little about everything remaining. Technology itself adds another uncertainty. Human civilization has used powerful radio communication for barely more than a century. A civilization older by millions of years might consider radio primitive. Laser pulses could carry information instead. Other methods might exploit physics or engineering we have never developed. Some civilizations could deliberately minimize detectable leakage as communication systems become more efficient. Time makes Kepler-452 especially difficult to interpret. If technological life there arose far earlier than ours, its radio broadcasting phase could have ended long before the light reaching Earth today began its journey. An ancient society might still exist while producing nothing recognizable to our radio telescopes. There are other possibilities. Technology may never have appeared there. It may have emerged and disappeared. A surviving civilization might transmit only locally or choose never to advertise its presence across interstellar distances. From Earth, those scenarios can produce the same observation, no detectable transmission. The absence, therefore, remains scientifically useful because it eliminates certain kinds of sufficiently powerful radio signals during specific searches. Yet it cannot distinguish an empty world from one whose technology has simply moved beyond the narrow window through which we are listening. Place the histories of Earth and Kepler-452b beside each other, and their resemblance changes character. The familiar features remain, yet the clocks began at different moments. Earth formed approximately 4.54 billion years ago. Kepler-452 is about 6 billion years old, and its planet likely formed during the same early period of that system. When Kepler-452b was beginning its existence, our world had no surface, oceans, or atmosphere. Earth did not exist at all. Neither did the Sunday. The material that would eventually become our solar system remained part of the interstellar environment long before gravity assembled the familiar architecture around us. By Earth's formation, the distant planet may already have accumulated roughly 1.5 billion years of geological history. Its crust could have been reshaped repeatedly. Any atmosphere and oceans, if they existed, would already have experienced immense cycles of change. Then life appeared here. Evidence places Earth's earliest life at least 3.5 billion years ago, with some interpretations reaching farther back. At that stage, Kepler-452b may already have been between roughly 2.2 and 2.5 billion years old. If biology ever emerged there, its evolutionary history could already have been extensive. Earth changed slowly afterward. Around 2.4 billion years ago, the Great Oxidation Event transformed atmospheric chemistry as oxygen produced by microorganisms accumulated on a planetary scale. Kepler 452b Meanwhile, would have been approximately 3.6 billion years into its own history. The difference grows stranger when we reach complex organisms. About 600 million years ago, increasingly diverse, multicellular life was spreading through Earth's oceans. By then, Kepler-452b may have been around 5.4 billion years old. Its planet was already older than our Sun is today. These intervals are difficult to picture. Human civilization occupies only a tiny fraction of Earth's timeline. Against spans exceeding a billion years, entire technological histories could arise, transform, and disappear without leaving any event simultaneous with ours. Meanwhile, the host star kept evolving. Hydrogen fusion gradually altered its interior, increasing its luminosity over immense periods. The planet did not need to migrate dramatically for its environment to change. Its star changed around it. That distinction matters when we compare planetary ages. Orbital position describes where a world travels. Stellar evolution determines how that same location behaves across geological time. A favorable orbit during one era can receive substantially different energy much later. Kepler 452b, therefore, occupies a timeline Earth has not reached. We see a planetary system roughly 1.5 billion years further through the life of a sun-like star. Whatever happened on its planet remains unknown, but the stellar clock itself is measurable. Our solar system follows the same broad physics. The sun also brightens as it ages. Kepler-452b shows us how much can change while a planet continues circling almost exactly where it began. The sun still has billions of years before becoming a red giant, yet Earth's habitability will end much sooner. At roughly 4.6 billion years old, our star remains on the main sequence, steadily fusing hydrogen in its core. That process gradually changes the core's composition. The result is a slow increase in solar luminosity. About 1 billion years from now, models place the sun near 10% brighter than today. Earth will continue orbiting at essentially the same distance, but the energy reaching its surface will rise. The habitable conditions we know depend on a narrower balance than the sun's remaining lifetime might suggest. Increasing sunlight accelerates evaporation. More water vapor enters the atmosphere, where it traps additional heat and encourages further evaporation. Over roughly the next 1 to 1.5 billion years, this feedback is expected to place growing stress on Earth's oceans and climate. Long before complete ocean loss, the biosphere faces another problem. Silicate weathering removes carbon dioxide from the atmosphere. As solar output rises, faster weathering can drive atmospheric carbon dioxide downward. Photosynthetic organisms that depend upon sufficient carbon dioxide eventually struggle. Plants using certain photosynthetic pathways are especially vulnerable as concentrations fall. Their decline would reshape food webs built upon primary production. Estimates vary with climate and biological assumptions. Still, many models give complex surface life, perhaps several hundred million to roughly 1 billion years before conditions become increasingly restrictive. Microbial organisms could persist much longer in protected environments. Habitability would therefore disappear unevenly, ecosystem by ecosystem, rather than ending everywhere at once. Farther into Earth's future, increasing solar energy could produce a moist greenhouse. In this state, the upper atmosphere becomes rich in water vapor. Ultraviolet radiation can split water molecules there, allowing lightweight hydrogen to escape into space. Given enough time, Earth's great reservoirs of surface water could be severely depleted. By roughly 2 to 3 billion years from now, model outcomes become increasingly dependent on uncertain feedbacks. Clouds, atmospheric circulation, geological cycling, and the evolving carbon dioxide inventory all influence the timing. The direction, however, follows directly from stellar evolution. A brighter sun steadily narrows the environmental range available to surface water and complex life. This gives Kepler-452b an unusual place in our comparison. Its host star is approximately 1.4 billion years older than the Sun and broadly similar in stellar character. If its planet began with Earth-like oceans, atmosphere, and geological regulation, it may have traveled farther along a comparable climatic path. We cannot know whether that happened. Its atmosphere and surface remain beyond direct measurement. Yet you can see why its age matters so much. Kepler-452b occupies a stellar system resembling a later chapter of our own, while the light reaching us has crossed roughly 1,400 years of space. In that distant system, processes expected eventually around Earth may already have had far longer to unfold. Venus gives us something distant. Exoplanets cannot. A neighboring world whose climate history can be studied directly. Its diameter is about 95% of Earth's, while its mass reaches roughly 81.5%. In bulk dimensions, the planets are remarkably similar. Their histories became radically different. Some climate models suggest early Venus could have supported surface water for hundreds of millions, perhaps even billions, of years. Other studies find much less favorable beginnings. The evidence remains incomplete. Yet if long-lived oceans existed, their duration may have offered ample time for chemistry, geology, and potentially biology to develop. The sun itself changed throughout that interval. As its luminosity increased, Venus received progressively more energy. Rising evaporation would have placed additional water vapor into the atmosphere. Water vapor is a powerful greenhouse gas, so greater atmospheric concentrations trap more heat. More heat then encourages further evaporation. Eventually, that feedback can become self-sustaining. Once water reaches the upper atmosphere, ultraviolet radiation separates its molecules. Lightweight hydrogen can then escape into space. Over geological time, this process removes one of the ingredients needed to rebuild oceans. Meanwhile, carbon dioxide released through geological activity can accumulate when liquid water is no longer available to support efficient rock weathering. Modern Venus shows the resulting extreme. Average surface temperatures approach 900 degrees Fahrenheit. Atmospheric pressure at the surface is approximately 92 times Earth's. Carbon dioxide dominates the atmosphere, while clouds containing sulfuric acid cover the planet above. No ocean remains to restore the earlier climate. Venus orbits at roughly 0.72 astronomical units from the Sunday. Kepler-452b travels at approximately 1.05 astronomical units from a star around 20% more luminous than ours. Those orbital distances alone cannot determine climate. Atmospheric chemistry, clouds, surface reflectivity, geological cycling, and planetary history all modify how incoming energy affects a surface. That uncertainty matters enormously here. Kepler-452b receives more stellar energy than modern Earth, placing its hypothetical climate closer to conditions where greenhouse feedback becomes increasingly important. Venus demonstrates that a terrestrial planet can cross climatic thresholds and become profoundly different while remaining physically similar in size and composition. But there is no evidence that Kepler-452b actually followed this route. We cannot measure its surface water, atmospheric pressure, or geological activity. Plate tectonics could matter because active crustal recycling may help regulate carbon dioxide through long-term interactions among rocks, atmosphere, and volcanism. Whether Venus ever operated such a system remains debated, and Kepler-452b's interior is entirely inaccessible. So Venus provides a physical precedent rather than a photograph of Kepler-452b's fate. It shows you how planetary habitability can disappear under increasing stellar energy. Two worlds can begin with comparable ingredients, then separate dramatically as climate feedbacks accumulate across geological time. By the middle of the 2020s, Kepler 452b had become one member of an enormous planetary census. The National Aeronautics and Space Administration Exoplanet Archive had passed 5,700 confirmed worlds. Thousands of planets now occupy categories that were entirely hypothetical within living memory. Yet the catalog is uneven. Small planets are harder to find than large ones, while long orbital periods demand years of observation. Worlds receiving Earth-like levels of stellar energy are especially difficult when they circle stars resembling the Sunday. Their transits happen infrequently, and each crossing produces only a slight reduction in starlight. That makes Kepler 452b unusual. Its radius is approximately 1.63 times Earth's, placing it outside stricter definitions of an Earth-sized planet. Researchers often reserve that description for worlds between roughly zero point 0.8 and 1.25 Earth radii. Kepler 452b instead earns its Earth-like reputation primarily from its orbit and Sun-like host star. Most potentially temperate planets we know occupy very different systems. Red dwarfs, the smallest and most numerous ordinary stars in the galaxy, dominate many habitable zone discoveries. Their low luminosity places potentially temperate orbits much closer to the star. That arrangement also makes planets easier for us to detect. But proximity brings complications. Many red dwarfs produce energetic flares, especially while young. Their nearby planets can experience intense radiation capable of altering atmospheres. Close orbits also encourage tidal locking, where a planet rotates once during each orbit and keeps the same hemisphere facing its star. Climate models show that tidal locking does not automatically prevent habitability. A substantial atmosphere or ocean could redistribute heat between hemispheres. Still, these systems differ profoundly from Earth's familiar arrangement. Consider the TRAPPIST-1 system, roughly 40 light-years away. 7 known planets with sizes broadly comparable to Earth orbit its cool red dwarf star. Several receive amounts of stellar energy that make them important targets for atmospheric studies. Their relative proximity also makes detailed observations far more practical than anything possible for Kepler 452b. Sun-like stars present another challenge. They are larger and brighter, so a small planet blocks a smaller fraction of their light. Habitable zone orbits also take much longer to complete. Detecting repeated transits, therefore, requires patience, precision, and favorable orbital alignment. This is where Kepler 452b retains its distinctive place. Its importance does not come from being the smallest, potentially temperate planet, nor the nearest. Many other worlds surpass it by those measures. Instead, we find a planet following an almost yearly orbit around a star broadly comparable to our Sunday. Among the thousands of confirmed exoplanets, that particular combination remains difficult to identify. The wider catalog has revealed that small planets and potentially temperate environments are widespread. Kepler-452b represents a narrower resemblance, one built around the architecture of the Earth and Sun relationship itself. Reaching Kepler 452b begins with an unforgiving equation. Every increase in speed demands energy, and interstellar distances magnify that demand beyond anything our spacecraft have encountered. Chemical rockets, which carried humans to the moon and probes toward the outer planets, cannot bridge such distances efficiently. Their exhaust velocities are simply too low. Nuclear energy offers a different scale. Project Orion, studied during the 1950s and 1960s, proposed detonating nuclear explosives behind a massive spacecraft. A reinforced plate would absorb each pulse and convert repeated explosions into acceleration. Advanced versions were theoretically capable of reaching several percent of light speed. Even at 3%, Kepler 452b would remain more than 46,000 years away. At 10%, the crossing still requires roughly 14,000 years. Fusion propulsion could push farther. Instead of splitting heavy atomic nuclei, fusion combines light nuclei and releases enormous energy. Designs such as Project Daedalus explored using fusion reactions to propel robotic interstellar spacecraft. If future engineering produced vehicles approaching 10% of light speed, you would still measure the journey in 14 millennia. Much lighter probes offer another possibility. Breakthrough Starshot studies laser-driven sails, where powerful lasers accelerate extremely small spacecraft without requiring them to carry conventional fuel. Proposed systems target roughly 20% of light speed. At that velocity, a probe would need about 7,000 years to reach Kepler 452b. Arrival creates another problem. A tiny laser sail carries little capacity for braking. Without a separate deceleration method, it would cross the planetary system at tremendous speed, gathering observations during a brief encounter before continuing into interstellar space. Antimatter represents an even greater energy density. When matter meets antimatter, their mass can be transformed into other forms of energy with extraordinary efficiency. In principle, advanced propulsion using this process might reach substantial fractions of light speed. At 50% of light speed, the voyage would still take roughly 2,800 years as measured from Earth. Producing, storing, and controlling the required antimatter remains far beyond present technology. A crewed journey introduces problems that propulsion alone cannot solve. Generation ships would need functioning ecosystems, durable machinery, genetic diversity, medical capability, and social stability across thousands of years. The people reaching the destination could be descendants separated from the original travelers by hundreds of generations. General relativity permits stranger mathematical possibilities. Wormholes could hypothetically connect distant regions of space-time, while proposed warp geometries alter space-time around a vessel. Known formulations require extraordinary physical conditions, including forms of negative energy that have never been shown usable at macroscopic scales. So when we imagine traveling to Kepler 452b, physics sets the scale. No existing propulsion system can carry us there within a human lifetime. Reaching it would require technologies, energy systems, and civilization scale endurance that humanity has not yet developed. For Kepler 452b, water is a question of history. If the planet is rocky, its present supply depends partly on what happened while the system was forming. Water can arrive inside volatile rich asteroids and planetary building blocks, originating beyond the region where ice remains stable. Comets can contribute as well. Earth appears to have acquired much of its water from such material during its early development, although the exact proportions and timing remain actively studied. Kepler-452b formed at roughly 1 astronomical unit from a sun-like star. That places its birthplace within a thermal environment broadly comparable to Earth's early neighborhood. Farther outward, beyond the frost line, water ice could survive inside growing bodies. Gravitational scattering could then send some of those objects inward, supplying young rocky planets with water and other volatile compounds. A larger planet changes those encounters. If Kepler 452b carries several Earth masses, its stronger gravity would increase its ability to capture passing material during formation. That could have delivered a substantial inventory of water, yet possession and preservation are separate problems. Any surface ocean would now exist beneath greater stellar energy than Earth receives. More heating encourages evaporation, adding water vapor to the atmosphere. Clouds could become extensive, precipitation could intensify, and the entire water cycle might transport more energy between surface and atmosphere. Depending on cloud properties, some incoming starlight could be reflected away. Water vapor itself, however, is a powerful greenhouse gas. Higher in the atmosphere, another process becomes important. Ultraviolet radiation can split water molecules through photodissociation, meaning energetic light breaks molecules apart. Hydrogen produced this way is extremely light. Once it reaches the upper atmosphere, some can escape into space. The remaining oxygen may react chemically with rocks, rather than accumulating indefinitely overhead. Mars shows how dramatically planetary water can diminish, although its history involved several processes. Low gravity made atmospheric escape easier, while the loss of a strong global magnetic field left its upper atmosphere more exposed to the solar wind. Measurements by the Mars Atmosphere and Volatile Evolution mission have shown that atmospheric loss continues today. Kepler 452b presents almost the reverse gravitational situation. Greater gravity should make atmospheric escape harder, helping the planet retain gases and potentially preserve water longer. But its older, brighter star supplies stronger energy to the planetary climate, increasing the possibility of sustained evaporation and water reaching vulnerable atmospheric heights. So if you could somehow stand above this unseen world, an ocean would not be guaranteed by its orbit. Its existence would record billions of years of delivery, geology, atmospheric chemistry, and escape. We can estimate each process from physics. We cannot yet determine their final balance there. Water may remain across its surface, survive beneath it, linger mainly as vapor, or have been depleted long ago. The available observations cannot distinguish among those histories. Deep beneath a rocky planet, motion can determine what survives above. On Earth, molten iron circulates through the outer core as the planet rotates. Those electrically conducting currents generate our global magnetic field through a process called the geodynamo. Far beyond the surface, that field forms the magnetosphere, a vast region where charged particles are redirected around Earth. The incoming particles belong largely to the solar wind. This continuous stream flows outward from the Sun and interacts with every planet it encounters. Earth's magnetosphere diverts much of that flow. Atmospheric particles can still escape through several processes, but magnetic shielding changes how the upper atmosphere interacts with its star. Mars offers an important comparison. Evidence preserved in ancient Martian rocks indicates that the planet once possessed a global magnetic field. Its internal dynamo faded more than 4 billion years ago. Atmospheric loss then continued as solar radiation and the solar wind interacted with the increasingly exposed upper atmosphere. Mars gradually lost much of the thicker atmosphere and surface water it possessed early in its history. For Kepler-452b, we cannot perform the same reconstruction. No measurement reveals whether a global magnetic field surrounds the planet today. At roughly 1400 light years, its magnetosphere lies far beyond the sensitivity of existing observational techniques. Even establishing whether its interior remains geologically active requires inference. Yet its possible structure gives us clues. A rocky planet several times Earth's mass could retain substantial internal heat for billions of years. Radioactive elements within its mantle would provide additional heating. If the core remains sufficiently fluid and convective, vigorous circulation could sustain a geodynamo. Some models of super-Earth interiors therefore allow magnetic fields comparable to Earth's or potentially stronger. That possibility matters under an aging sun-like star. A substantial magnetosphere could reduce direct interaction between stellar wind particles and the upper atmosphere. Combined with stronger surface gravity, such shielding might improve atmospheric retention over geological timescales. But greater mass changes the interior in other ways. Pressure rises dramatically with depth. Mantle minerals behave differently, and convection may become slower under some interior models. Plate tectonics could weaken or operate through unfamiliar regimes. Without efficient recycling between the crust, mantle, and atmosphere, long-term regulation of carbon dioxide could change profoundly. Venus reminds us that planetary size alone settles none of this. Although similar to Earth in diameter and mass, Venus lacks an Earth-like global magnetic field today and shows no present system of moving tectonic plates comparable to Earth's. Kepler-452b may possess the entire linked machinery, a convecting metallic core, magnetic shielding, active geology, and atmospheric recycling. It may possess only fragments of that system. From our present distance, both possibilities remain scientifically defensible. The shield that could have protected its atmosphere for billions of years is also one of the planetary features we cannot currently see. On July 23, 2015, Kepler-452b entered public view through unusually careful language. At the National Aeronautics and Space Administration Ames Research Center in California, scientists presented a planet whose measured properties made it exceptional. Their claims were significant, but deliberately limited. The announcement described Kepler-452b as the smallest planet then discovered orbiting within the habitable zone of a sun-like star. That phrase carried several qualifications. A habitable zone identifies orbital distances where liquid surface water could be possible under suitable atmospheric conditions. It does not establish that water exists there. National Aeronautics and Space Administration Administrator Charles Bolden emphasized the planet's resemblance to Earth within that specific context. John Jenkins, who led the Kepler data analysis effort, called the discovery a milestone in the search for planets like our home. The wording mattered. Neither statement established habitability, biology, oceans, continents, or an Earth-like atmosphere. The scientific paper was equally restrained. Jenkins and his colleagues published their analysis in the Astronomical Journal under a title identifying Kepler 452b as a super-Earth in the habitable zone of a sun-like star. The measured radius was approximately 1.6 times Earth's radius. That alone left its composition uncertain. Then the story moved beyond the scientific paper. News reports rapidly adopted simpler descriptions. Phrases such as Earth's twin and Earth 2.0 appeared across coverage, turning a statistical resemblance into something visually familiar. You can see why those labels traveled easily. A planet circling a sun-like star on an almost yearly orbit requires little imagination to picture as another Earth. But the data never supplied that picture. Its larger radius meant the planet might possess a rocky surface, yet a substantial, volatile envelope remained possible. No atmospheric composition had been measured. Surface pressure was unknown. Liquid water had never been detected. Temperatures depended strongly on atmospheric assumptions that observations could not constrain. Within the broader online discussion, speculation soon extended toward life and technological civilizations. Those possibilities were scientifically imaginable in the broadest sense, but they were not discoveries reported by the Kepler team. Each additional claim moved farther from what the telescope had actually measured. That distinction reveals something important about how distant planets reach us. Scientists work with probability distributions, uncertainties, model assumptions, and carefully bounded conclusions. Headlines work under different pressures. A phrase like potentially rocky requires explanation. Earth's twin creates an image instantly. Kepler-452b, therefore, acquired two identities in 2015. One belonged to the measurements, a larger than Earth planet with a remarkably familiar orbit around a sun-like star. The other emerged through public retelling, where possibility gradually hardened into imagery. When we separate those identities again, the discovery loses none of its scientific importance. Its actual measured properties were already extraordinary enough. Kepler 452b becomes more revealing when we stop treating it as an isolated discovery. The Kepler mission watched enough stars for long enough to ask a broader question. How often does nature build planets with some of Earth's basic characteristics? Astronomers describe this through an occurrence rate, the fraction of stars expected to host planets within chosen ranges of size and orbital energy. For potentially Earth-like worlds around Sun-like stars, this quantity is often called eta Earth. Calculating it is difficult. Kepler detected only planets whose orbits happen to cross their stars from our viewpoint, and detection becomes harder for smaller planets with longer years. Scientists therefore correct for worlds Kepler would have missed. Different assumptions about planet size, habitable zone boundaries, stellar properties, and detection completeness produce different estimates. Some influential analyses have placed the occurrence rate near 22% under particular definitions, although later studies span a broader range. The uncertainty matters, yet the underlying implication remains enormous. The Milky Way contains roughly 200 billion stars. Around 7% are broadly sun-like stars of spectral class G, giving approximately 14 billion such stars across the galaxy. If roughly 22% hosted a suitably sized planet in a temperate orbit, the arithmetic would suggest around 3 billion candidates. Those are not 3 billion inhabited Earths. They are not even 3 billion confirmed habitable planets. Each would carry unanswered questions about atmosphere, geology, water, magnetic fields, and planetary history. The statistical category describes where a planet is and how large it appears, while habitability depends on much more. Still, the numbers transform our perspective. Before exoplanet surveys, we had one known example of a rocky world supporting life. Kepler showed that planetary systems are abundant, and small planets occur throughout the galaxy. A world occupying an Earth-like orbit around a sun-like star no longer has to be treated as an extraordinary architecture. Statistics also suggest that examples may exist much closer than Kepler-452b. Depending on the adopted occurrence rate, estimates can place the nearest temperate, roughly Earth-sized planet around a Sun-like star within only a few tens of light years. The exact distance remains uncertain because nearby surveys have not yet produced a complete census. This is where one distant planet acquires unusual value. A probability cannot orbit a named star. Kepler 452b can. We can assign it a measured year, radius, host star, and position in a real planetary system. It turns a population estimate into something specific enough to study. So the galaxy suggested by Kepler is populated with possibilities rather than guarantees. Kepler 452b is one measured point within that enormous distribution. Its importance comes partly from its individuality and partly from what its existence says about how many comparable worlds may remain unseen. The next great leap in exoplanet science may leave Kepler 452b almost exactly where it is today. New observatories will find smaller worlds, study nearby atmospheres, and search for chemical traces of biology. Yet, distance determines which planets can surrender their details, and this one lies about 1,400 light years away. The Nancy Grace Roman Space Telescope is designed to expand our knowledge of planetary populations through gravitational microlensing, where a foreground star briefly magnifies light from a more distant star. That technique can reveal planets at orbital distances difficult for transit surveys to reach. Roman will greatly enrich the statistical picture of planetary systems, although Kepler 452b is not a primary target for atmospheric characterization. A more direct approach is taking shape through the Habitable Worlds Observatory. The National Aeronautics and Space Administration is developing this future concept to image potentially Earth-like planets around nearby Sun-like stars. Its instruments would separate faint planetary light from overwhelming starlight, then examine that light for atmospheric chemistry. A coronagraph, an optical system that suppresses a star's glare, is central to that ambition. For Kepler 452b, geometry works against us. At 1,400 light years, the apparent separation between planet and star is extremely small. The planet itself is also extraordinarily faint. Habitable Worlds Observatory targets will therefore favor much closer systems where direct imaging offers a realistic chance of collecting useful photons. Europe is pursuing another route. The European Space Agency's PLA-Natary transits and oscillations of stars mission is planned to search large regions of the sky for planets around bright stars. It will also measure stellar oscillations, allowing astronomers to determine stellar ages and properties with unusual precision. Those measurements should sharpen our understanding of Earth-like planets around Sun-like stars, especially among comparatively nearby systems. But improved exoplanet science does not guarantee improved knowledge of every known world. No currently planned mission is expected to reveal Kepler 452b's atmosphere, oceans, continents, clouds, or biological activity. The discovery measurements from the Kepler mission, therefore, remain the foundation of what we can say about it. Over the next 20 to 50 years, our maps of nearby planetary systems should become far richer. You may see atmospheric spectra from worlds whose temperatures and sizes resemble Earth's. We may even identify compelling biosignature candidates around other stars. Kepler 452b could remain beyond those advances. That creates an unusual scientific legacy. We found a planet with an exceptionally Earth-like orbital relationship around a Sun-like star, yet placed too far away for the detailed observations that modern astronomy increasingly demands. As our instruments become more capable, they will likely teach us through nearer worlds, while Kepler-452b remains defined largely by the precious measurements that first revealed it. A planet can become meaningful long before we know what its surface looks like. Kepler 452b demonstrates that unusually well. Its atmosphere remains unknown, its composition uncertain, and life there has never been detected. Yet its measured relationship with its star places it unusually close to a pattern we recognize. That pattern begins with rhythm. Kepler 452 is a Sun-like star, and its known planet completes an orbit in roughly 385 days. Its orbital distance also resembles Earth's arrangement around the Sunday. Individually, those similarities are measurements. Together, they create something our minds immediately notice: familiarity. Human cognition is built to recognize patterns. We compare new things with known things, searching for relationships that make unfamiliar information easier to understand. In a galaxy containing hundreds of billions of stars, some planetary systems should naturally resemble ours through statistics alone. Still, knowing that does not erase the effect. When you hear of another world circling another sun-like star on an almost Earth-like schedule, abstraction becomes easier to imagine. That response does not weaken the science. It reveals how scientific knowledge enters human culture. Numbers acquire context, comparisons acquire meaning, and distant objects become part of our shared mental geography. Kepler 452b gained that position almost immediately after its announcement on July 23, 2015. The timing carried historical resonance. 46 years earlier, during July of 1969, Apollo 11 had placed humans on the moon. One achievement involved physically crossing the space between neighboring worlds. The other involved detecting a planet roughly 1,400 light-years away, without ever seeing its surface directly. Between them lies a striking measure of how astronomical exploration had changed. Consider what the Kepler team actually accomplished. A telescope watched a distant star and recorded tiny, repeated reductions in its brightness. From those changes, researchers derived an orbital period precise to a fraction of a day. Measurements of the star then helped establish its temperature, size, age, and evolutionary state. Those pieces allowed scientists to estimate the environment in which the planet travels. We never received a photograph of continents. No probe entered its atmosphere. Instead, careful measurement turned variations in starlight into knowledge about a world whose light has traveled for roughly 14 centuries before reaching us. That achievement says something about the observers, as well as the observed. Humans developed mathematics capable of describing orbital motion, instruments sensitive enough to measure minute changes in brightness, and scientific methods designed to separate evidence from expectation. We can recognize resemblance while still marking uncertainty. Kepler 452b, therefore, occupies an unusual place in our imagination. Its importance comes partly from what has been measured, and partly from the mind encountering those measurements. Across an immense distance, we found a planetary arrangement that echoes our own, then learned enough to understand exactly where the resemblance ends. A planet does not remember through stories. If Kepler 452b is rocky, its memory would be physical, compressed into minerals, sediments, ancient crust, and chemical ratios accumulated across roughly 6 billion years. Each layer would preserve conditions from a different stage of its star's life. The deepest surviving rocks might belong to an unfamiliar beginning. Kepler-452 would have been younger and less luminous, delivering less energy to the planetary surface. Minerals formed during that era could preserve traces of ancient oceans, atmospheric chemistry, volcanic activity, and perhaps the earliest interactions between water and crust. Higher layers would carry later chapters. If the planet enjoyed a prolonged temperate period, sedimentary deposits might record repeating cycles of rainfall, erosion, ocean chemistry, and climate change. Volcanic rocks could mark episodes when material rose from the interior. Impact layers might preserve collisions separated by hundreds of millions of years. Then the stellar environment would gradually change. As Kepler-452 aged, hydrogen fusion altered its internal structure and slowly increased its luminosity. The planet received progressively more stellar energy. Any geological thermostat operating at the surface would have been forced to respond across immense spans of time. A geologist standing there could search for those responses directly. Stratigraphy, the study of layered rocks through time, would establish the sequence. Isotope ratios could reveal ancient temperatures, atmospheric changes, and interactions between water and minerals. Mineral assemblages, groups of minerals formed under particular conditions, could expose transitions that telescopes cannot resolve. If oceans began disappearing, their retreat might leave enormous deposits behind. Altered minerals could preserve episodes of intense evaporation. Changes in oxidation might reveal atmospheric transformation. The youngest rocks would represent conditions under the brighter star we observe today. Life, if it ever emerged, could leave another category of evidence. Fossil structures might survive within ancient sediments. Organic molecules could remain protected inside favorable minerals. Isotopic fractionation, where biological processes favor certain forms of an element, might reveal activity even when recognizable fossils had vanished. Earth's Precambrian rocks preserve comparable clues from organisms living more than 3 billion years ago. A rocky Kepler-452b could contain an even longer archive. What would you find if you could examine its oldest surviving shoreline? That question reaches the boundary between what exists and what astronomy can access. From roughly 1,400 light years away, no telescope can examine individual rock layers or collect mineral samples. We can measure the star and infer pressures placed upon its planet, yet the geological record itself remains inaccessible. For 6 billion years, the planet has traveled around a changing star, while its surface continually recorded the consequences. Somewhere within its crust may lie evidence of warmer seas, lost atmospheres, extinct ecosystems, or an entirely lifeless history. The rocks would distinguish those possibilities. Their record spans the stellar aging process that Earth itself continues to enter, written across planetary time. Every civilization lives inside a clock it did not build. Its star sets that clock through nuclear fusion, gradually changing brightness, temperature, and eventually size. If intelligence survives long enough, stellar evolution stops being distant astronomy. It becomes an environmental constraint affecting the civilization itself. Kepler 452b gives that constraint a planetary form. If life ever developed there, and if some branch became technological, its world would have faced the consequences of an aging sun-like star earlier than Earth will. The fundamental choices eventually narrow. A civilization can adapt its world, leave it, or disappear with the conditions that once supported it. Adaptation would require planetary engineering on an extraordinary scale. Increasing planetary reflectivity could reduce absorbed stellar energy. Atmospheric composition might be deliberately altered. Carbon cycles could be managed through technologies operating across continents and geological timescales. Such interventions resemble terraforming in reverse, preserving an existing biosphere instead of transforming an alien environment into a habitable one. Precision would matter enormously. Climate systems contain interacting oceans, clouds, rocks, gases, ice, and living organisms. Changing one component could produce consequences elsewhere. Maintaining habitability beneath a steadily brightening star might therefore require continuous management extending far beyond the lifetime of any government, culture, or technological institution humans have created. Migration offers another path. A civilization could move outward within its planetary system as warmer conditions spread across inner worlds. Eventually, survival beyond the aging star might demand interstellar settlement, yet the propulsion limits we encountered earlier remain unforgiving. Crossing light years requires enormous energy, durable technology, and planning across timescales that challenge civilization itself. Without either response, stellar evolution continues anyway. There need be no sudden catastrophe. A main sequence star naturally becomes brighter as conditions inside its core evolve. Oceans, atmospheric chemistry, and biological productivity respond over immense periods until familiar ecosystems can no longer persist. Earth participates in the same process. Estimates suggest complex surface life may have roughly 500 million to 1 billion years before. Increasing solar luminosity and declining carbon dioxide make present ecosystems increasingly difficult to sustain. 500 million years seems almost beyond comprehension. Yet roughly that span separates us from the Cambrian explosion, when complex animal life expanded dramatically through Earth's oceans. Seen against planetary history, even enormous intervals eventually become completed chapters. Neither Earth nor Kepler-452b selected its starting conditions. Gravity placed matter into orbit, planetary formation supplied the materials, and stellar physics established the changing energy budget. For almost all of Earth's history, life simply existed within those boundaries. Then one species developed the ability to calculate them. We can measure the sun's age, model its future luminosity, estimate Earth's remaining biological window, and recognize similar processes around distant stars. That knowledge changes nothing about stellar physics, but it introduces something rare into the equation: foresight. Kepler 452b therefore places finitude on a cosmic scale. Intelligence may never defeat stellar evolution, yet understanding it creates the possibility of response. Whether awareness ultimately becomes escape, adaptation, or merely knowledge of the boundary remains unresolved. A measurement can outlive the machine that made it. Kepler 452b remains inside humanity's records, even though the telescope that found it no longer gathers starlight. What survives is a remarkably precise trace of something we cannot visit, photograph, or examine directly. From roughly 1,400 light-years away, its repeated passage across its star revealed a year lasting about 385 days. That precision sits beside enormous uncertainty. The planet circles an older, sun-like star and receives somewhat more stellar energy than Earth. Its measured size places it between familiar categories. We cannot see its surface. Its atmosphere remains beyond measurement. Whether oceans, continents, clouds, or barren terrain occupy that distant world cannot yet be established. The Kepler Space Telescope itself completed its work years ago. After exhausting the fuel needed to control its orientation, the National Aeronautics and Space Administration retired the spacecraft on November 15th, 2018. Kepler remains in orbit around the Sun, following its own path through interplanetary space. Its scientific work did not end there. During nearly a decade of observations, Kepler recorded immense collections of stellar brightness measurements called light curves. Each one traces how a star's brightness changes over time. Researchers continue examining those records, refining planetary candidates, and extracting information that was already captured before the spacecraft ceased operating. There is something unusual in that arrangement. The instrument can no longer observe, yet discovery continues through its archived observations. New analytical techniques can revisit old measurements. Improved statistical methods can separate planetary signals from stellar behavior or instrumental effects. A telescope's productive lifetime can therefore extend far beyond its final transmission. Kepler-452b occupies a special place within that inheritance. Its orbital resemblance to Earth around a sun-like star remains unusually compelling, although better matches almost certainly exist. Finding them depends upon geometry, observing time, sensitivity, and chance. The galaxy does not arrange its planets for convenient detection. Future instruments will search differently and closer. Eventually, another world may match Earth more precisely in size, orbit, stellar environment, or several properties together. Such a discovery would not erase this one. Instead, another close match would add evidence that familiar planetary arrangements can emerge repeatedly from the same physical laws. And that is where the resemblance becomes most useful. Gravity follows the same principles around every star. Matter responds to radiation everywhere. Planets form from disks, atmospheres evolve, stars age, and orbital motion continues without regard for the meanings observers attach to it. You can interpret that consistency in many ways. Science does something narrower. It measures what reaches us, tests what those measurements permit, and leaves unsupported possibilities open. Far beyond our instruments, Kepler-452b continues around its star. One orbit follows another, as it has across billions of years. We entered that history only recently, when a small change in distant starlight reached a telescope and became something humans could recognize. The planet was always there, only now do we know to look.